this started out as a comparison of the Tstatistic Design, which exists in this phase 2 dose finding software product that we have called Compass. I've been hearing all about, and we've been implementing the mTPI, the BLRM, and the CRM in East. And I know about the Tstatistic Design, and I've used it, and I'll tell you what it is later, but I wanted to compare it to these other 3 designs in East and see how it performed for dose finding, for finding maximum tolerated dose. And as a byproduct, you get a comparison of mTPI, BLRM, and CRM. So that's the motivation. mTPI is appealing and popular because it's easy to implement, it's efficient versus those other 2 designs which you'll see, and is much better than 3+3. The T-statistic design is appealing and popular for the same reasons. It's easy to implement, it's efficient versus Bayesian 4-parameter logistic Emacs model and NDLM. That doesn't mean it's better, it competes with them. And it's obviously better than fixed randomized designs. So the aim was to compare T-statistic design to the other designs. To do that, I selected a spectrum of true underlying dose response curves. They're plotted here, there are 5 of them. This middle curve is a default linear curve that's in East, and then there's a left shifted curve and a right shifted curve, and then there's an extreme high and an extreme low curve. So if you don't know what your drug does, you might want to simulate a whole set and see how the designs do across a whole set. If you have some reason to pick on one of these, then you just want to focus in that region. So the design parameters for this simulation comparison were 7 doses, just numbered 1 to 7, 30 subjects, 10 sequential cohorts of 3 subjects each. The first cohort starts at dose 1. Each subsequent cohort is assigned a single dose per the adaptive design. The target toxicity level is 0.3, and the number of simulations were 10,000 in East and 1,000 for the T-statistic design, because I had to do some of the calculations of the performance characteristics by copying the simulation results into Excel, and it got bogged down with too many simulations, so I limited it to 1,000. The parameters for the mTPI setup were 0.25 cutoff for underdosing, 0.25 to 0.35 for on target, and 0.35 for overdosing. The prior was a beta 1,1 prior for the true target toxicity at each dose. There's one thing to keep in mind is mTPI models the probability at each dose. It doesn't restrict them to be monotonically increasing, which is an advantage of the model-based design because they're monotonic. And then the T-statistic design, which you will see, assumes a monotonic relationship. So part of the mTPI's underperformance might be its lack of assumption of monotonicity, and there's a way to get around that I'll hint at the end. The overdosing exclusion rule, I wanted to yield a full sample size. So if the probability of toxicity at any dose is greater than the target probability, that had to exceed 0.999 in order to exclude a dose, and it'll never get there. So I always got the full sample size. But then I wanted to investigate the overdosing exclusion rule, and I used a setting of 0.6 for that probability. I have a couple of slides for how this looks in East. You're going to see that later, I think, this afternoon, so I'm going to skip those in the interest of time. After I got my initial results using those default settings, those were the default settings in East, I spoke to Anastasia Ivanova about the results because she's the author on the T-statistic paper, and she said, well, you haven't optimized the mTPI designs or the BLRM or the CRM, and so in order to optimize them or to do some degree of optimization, I used two probabilities of early stopping. I required a 95% or an 80% probability for excluding a dose. And then I widened the range around the target dose. And then instead of using a beta 1-2, instead of using a beta 1-1 prior, I set the prior to be right at the target toxicity level. To influence the estimation around the target toxicity level. The T-statistic design works like this. It computes a T-statistic, which is like a binomial normal approximation to the binomial T, just difference from the target divided by a standard error. But it requires, it uses the isotonic estimates of the proportions at each dose. And then if the T is small, you increase 2 dose increments for the next cohort. If the T is moderately small, below 0, you increase 1 increment. If it's very tight to 0, then you repeat the dose. And the reason we choose the very tight interval is so we get the dose to go back and forth. Because usually the target toxicity levels between 2 doses, so if you stick at one, you know, we found it's better to bounce more than it is to stick. So that's why it's tight. And then if it's moderately large, greater than 0, we go up 1 dose increment. If it's very large, we go up 2 dose increments. I'm sorry, I said up, I meant down. I also widened the interval around repeating dose to see how that worked, because those are the 2 methods that we've been using. The second method sticks more at the same dose. The first method bounces more. So this is just a layout in COMPASS. It looks the same as the layout in EAST because it's built on the same architect framework. So the T-statistic design doesn't have any early stopping or early exclusion of doses. So Jaydeep Bhattacharya is a software engineer at Cytel. He's kind enough to implement that. And so I used these 2 dose exclusion rules. If the probability that the toxicity rate at a given dose exceeded 0.35 was greater than 0.8, I excluded the dose and never went above it. And then I did it a second way where I looked at the probability that it exceeds 0.5, and that had to be high to exclude it. And those original 2 designs were the no stopping. So for BLRM, the specifications are here. The underdosing limit was 0.25, the target interval 0.25 to 0.35, excessive toxicity is shown, and unacceptable greater than 0.45. As Ling mentioned, it's a bivariate log normal for the 2 logistic parameters. And the prior on the low dose was a 0.05 probability of DLT. The prior estimate of MTD was right in the middle, and there were 1,000 samples for the fitting. And then the probability of overdosing needed to be less than 0.25, which was the default setting. And I'll skip the setup. To optimize BLRM, I read the Neuenschwander paper, and he recommended 3 priors. I'm not going to go over those. They're listed in the slides. You could look them up later. Just in the interest of time, I used each of those 3 priors. the doses with overdose control probabilities, I looked at greater than 0.5, greater than 0.7, and greater than 0.9. So that was 9 combinations in all. These are the priors, which I'm going to skip because I want to spend time on the results. For CRM, the target toxicity level was 0.3. I used a one-parameter logistic model, and the prior probability of toxicity for each dose is what's shown there, which centers the target at dose 4 in the middle of the range. And the overdose rule was probability of toxicity greater than, exceeding the target greater than 0.6. And then I also evaluated a no early stopping rule. And the input slide looks, similar. There are the tabs, and Rishikesh is going to go over some of this afternoon, I think. For CRM optimization, I permitted skipping doses like the Tstatistic Design. I used these 3 priors that are listed there, and they're all increasing. And then I just wanted to use a flat prior to see what that did, and so there was a 4th flat prior as well. And there are 2 upper toxicity limits for the East default in the one-parameter logistic model, and I just kept them the same. So there were 6 configurations of CRM. This is just a verbal summary of the findings. Then I'm going to show you the detail, and then we'll go back to the verbal summary. But just to let you know what to look for in the results, the Tstatistic Design looked like a competitor to the 3 key designs in East, the mTPI, BLRM, and CRM. That's based on performance criteria, which included the probability of identifying the correct target dose, the probability of minimizing the probability of assigning subjects to doses above the true target. And then I spoke with Ina Perovskaya, who's got a lot of experience in this area, and she said, well, it's not only the probability of assigning subjects, it's actually the number of toxicities that you observe. You want to minimize that number. Obviously, these are correlated, but that's another measure. So I looked at that. And then the early indications from this set of simulations are that Tstatistic Design is competitive with the other 3 designs. When you consider performance across the spectrum of designs, I could find an mTPI or a BLRM or a CRM that was configuration that was better than the Tstatistic Design for 1 dose response curve or 2 dose response curves, but it performed less well on other dose response curves. So you'll see at the end, I propose 1 method for integrating the results, averaging the results across all 5 dose response curves. And that's the last slide. In summary, BLRM and CRM seemed better than mTPI for estimating target doses, but they assign more subjects above the target and result in generally more toxicity. So BLRM was more favorable to limit toxicity. And when you add all that up, you're going to see that mTPI came out better, a little better than BLRM or CRM. So now the numbers. This is the mTPI 1 is the one that has no turning off doses and yields the full sample size. The 0.6 uses that 0.6 cutoff. And then this mTPI opt, that's for optimal. That just gives the range of observations across all the configurations of mTPI that I ran. And then I picked the one mTPI configuration that was with the 95% probability for requirement for stopping a dose. And the 20 was the wide range, the one that was 0.1 to 0.5 for the target dose. So that wide range and a high probability of ruling out doses seemed to be the best performing mTPI configuration overall. That's that column. The BLRM default column, that's DF, that's the default settings in East, and then there's the optimum column, which gives the range of all of the cases of BLRM that I ran. And then the BLRM configuration, which did the best, was the one with the prior 10 and the 50% probability cutoff for excluding doses. And then there's the CRM default and the CRM optimal, and the best CRM among those four priors was the CRM with the second prior that you have to look back to see what it was, but that's that one. And then there are the two configurations of Tstat without the early stopping. I made this summary slide before we had the software implemented, so I didn't add the the exclusion of doses for overdosing option until later, and that comes on other slides. So while I was talking, I'm sure you looked through this and you could see that for some dose response curves, one design does better than another, and for other dose response curves, another does better. But in general, the Tstatistic design is competitive in the range, and many times at the top of the range for probability of selecting the correct MTD. And so here's the second criteria, the percent of subjects assigned to doses higher than MTD. And for the extreme high dose response curve, obviously we're going to assign some subjects to dose 1 because we're starting there, so that probability is the probability that the design assigns anything above dose 1. And obviously the low numbers here are good, and you can see that mTPI, the best mTPI design, the 120,90, that's the lowest one, and that did really well across the board. But Tstatistic competed with it in some cases, in the one case. And then it was within the range in all the other cases. But you notice that the BLRM and the CRM had pretty high values in some cases, which is not desirable. Now, there's a qualifying statement there. The criteria that was talked about and used and recommended is only a 25 or a low probability of exceeding the MTD. And I used a high probability. What's going to happen with the low probability is the probability of selecting the correct dose is going to go down because you're going to stop a lot easier and you're going to migrate toward lower doses. So the reason these are high is to get good performance on picking the right dose. It's a trade-off between permitting some allocation to doses that are too high in order to get that model to fit at the target dose versus protecting the subject. So that's the trade-off. And this is a kind of a situation where I'm trying to optimize. The last one is the actual numbers of DLTs. And here you can see again, it's the same sort of pattern that we saw on the last slide, where the mTPI does really well at lowering those things. And the BLRM and the CRM are a little higher, and the Tstatistic is on the low range towards the BLRM and the CRM, but on the high side in compared to mTPI. So now, I couldn't fit everything all on one slide, so what I did was I copied the ranges from the other designs onto this slide, and then I have these 4 configurations of the early stopping probabilities for the T-statistic design and for the T-statistic design. And so you can see when you put in the early stopping of doses for the T-statistic design, you deteriorate its ability to pick the correct dose, but not too much. When you look at the same setup for the percent of subjects assigned to doses higher than MTD, it does better. It improves the T-statistic design's performance in general, particularly with the narrow, when you don't stick at, when you have that minus 0.1 to 0.1 range for sticking. That looked better than the other one for the default linear, but not as good for the other 2. But again, it makes it more competitive with the mTPI design. And then the average number of DLTs was a little bit lower, but not that much lower with the early stopping of doses. So one way to rank across the designs, one way to rank the designs across the 5 dose response curves and the 3 performance criteria is to weight the first criteria 50% and then split the remaining 50% between the other 2 criteria, since those other 2 criteria are both safety criteria. The one criteria is picking the right dose, and the other 2 criteria are safety. So I just arbitrarily made it 50-50 and split the other 50 between the other 2. And this is the only configuration I ran. I promise it's the only one I ran. You know, other criteria are going to yield other results, perhaps. And then what I did was I computed the relative difference from optimal for each dose response curve scenario. For the first criteria, the probability of identifying the correct dose, a high value is good, so I took the difference from the observed correct, from the maximum correct across all the designs, and I took the ratio of that difference to the difference between the min and the max. So it's like the proportion, if you're at the maximum, the value is 1, and if you're at the minimum, the value is 0. So it scales everything on a 0 to 1. And then I did the same thing for each of the safety criteria, but in that case, it's the difference above the minimum. Now, then I computed the weighted average across all dose response curves, and values close to 0 indicate closer to optimal, and values closer to 1 indicate the worst design, and values 0.5 are halfway in between. On the left, you read this list. The left 2 columns are above the right 2 columns, and they're sorted by that overall average relative difference, weighted 50, 25, 25, and then averaged across all the 5 dose response curves. So when you look at the optimal value generated by any of the designs, the mTPI was best, and the T was second, and CRM and BLRM were as listed there. But that's kind of not fair because, you know, to take the optimum value for one design that's no good, not that good for another design, you know, you can get skewed results that way. The listing just output them, so I copied them in there. For the individual configurations, the T and the mTPI configurations that are listed there and the BLRM configuration default came out about the same, around 0.45, which isn't much better than being halfway. So it's kind of like you're bad for some DR curves, you're bad for others, but in general, you're a little bit better than 50%. With these configurations across that spectrum of dose response curves. And then the other cases, fall further across the range. The Tstatistic Design is as easy as mTPI to implement because you can make a table like this for the Tstatistic Design. Because once you have a number of toxicities and a number of subjects, the T is determined, and you can back calculate whether to go up or down 1 or 2 doses. And so it's a spreadsheet that exists. You fill in the yellow cells for the design, and you fill in the yellow target toxicity level, and then it populates the spreadsheet, and you can print it off. So that's an advantage, and it performs well. So it's a competitor in my mind. So back to the remarks, to sum up, the T-statistic design looks like a competitor to the 3 designs in East. And that's based on the 3 performance characteristics that we talked about. These are early indications that it's competitive across a spectrum of true underlying dose response curves. So if you don't know where you are, could be any of these extremes, it performs well. But if you can zero in on a particular 1 or 2, then you might be able to optimize the model-based designs or the mTPI to perform better. So the next steps are, I'm lobbying within Cytel to add T-statistic to East, and I think it's on the list over the next couple of years. You could consider other ranking mechanisms to, decide on ordering the performance characteristics of these designs. And you could evaluate additional design configurations to optimize. Because I don't have much experience with BLRM and CRM or mTPI, so I just did a little bit of reading and picked a few cases that made sense to me based on what I read. So I'm happy if anyone wants to collaborate to try and optimize the other designs to see how they perform. The question, though, that comes out of this, in my mind, is that I'm guessing that an isotonic Bayesian approach like that in Anastasia Ivanova's 2012 paper is going to perform really well, because it's not going to rely on the model-based stuff and the reliance on the different priors, and it's going to just fit an isotonic model, which is, fits any shape, but it's going to take advantage of the mTPI type properties, I think. The methodology does extend to binary. I reread the paper this morning, and so that sub-bullet needs to get excluded. But we don't have it in software, so I can't test it yet. The second to last bullet's really important because nobody's validated these results yet. They're just, my simulations and copying things to spreadsheets and calculating and summarizing. So it all has to be double checked, and I'm in the process of doing that before I submit it anywhere. And the references, some relevant references are here that you could take later. The G reference is the mTPI design, and the Neuenschwander gave the BLRM key reference. And all these are discussed, the other designs are discussed in the user manuals. So that's all.